Welcome everyone to GeoHug. So I'm just promoting you up as panelists. Please don't be shy. Come on through, get the cameras on, get the mics on. Very excited. We've got Craig Hart joining us today. But before we do get stuck into today's session, I would just like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation. And I'd like to pay my respects to the elders past, present, and future. And yes, I am very happy that we have Craig Hart with us today. So Craig is an exploration geologist who brings a worldly perspective to mineral exploration, decision-making, and problem-solving. He's the past director of the Mineral Deposit Research Unit at the UBC and currently consults and contributes to several exploration companies. And today's session is going to be such a good one as he shares his insights with us on expanding opportunities within intrusion-related gold models. So thank you so much, Craig, for joining us today. It's amazing having you here.
Oh, my pleasure. I'm super stoked to be here.
Oh, that's awesome. Before we do get stuck into your session, I was really curious to know what got you into geology in the first place.
It was I went to uni to be a biologist, and at the end of the first year, everybody's sort of packing up to go to their jobs, and I'm talking to all of my biologist friends, and what are you guys going to do? Oh, we're going to go measure lupins and collect bunny turds. I said, oh, does that pay well? No, no, no. We have to pay our own way. And I went and talked to my geologist friends, and asked them what they're going to do. Oh, we're going to go climb mountains, smash rocks, fly around in helicopters, and wrestle grizzly bears.
That sounds
And how
like
much does that pay? That's $100 a day. Okay. It was easy to make the decision right then and there.
I imagine so. That's so good. And yeah, you have had quite a big career, done all sorts of things. So I was very curious, maybe some career highlights, some travel highlights, some of your favorite memories.
These jobs that we have are fantastic. There's rocks all over the world. If you're a gold geologist, there's gold all over the world. And so, the demand for new ideas and new people and talent is incredible. So I think, it just opens up the whole world of opportunities for you to go places, either, you know, yourself because you like to wander, or because the company thinks that you're going to be a better asset by getting experience in a more worldly exposure. So, yeah, I've been lucky. I think I've worked in maybe 40 or 45 different countries and
Wow.
seen geology and mineral deposits and how people get the job done and what matters. And you're not staying in the five-star downtown, right? You're at the end of the road, like
Yeah, you're
you're
really in the
beyond the end
thick
of
of
the
it.
road. And
Yeah.
so you're talking to real people in real situations and yeah, being exposed to those opportunities has just been priceless.
Yeah, that's amazing. What would be some of your favorite geological beauties around the world?
I love process. Like I like to see active things happening in a rock, and to be able to go to some places and see, like that's why volcanic rocks are so cool, right? Because you can see and you can imagine all of the components that are putting into the eruption. And
Yeah.
in drill core, people don't think about it as being that exciting, but when you think of the forces that have modified some of those rocks through ore forming processes, I'm continually blown away with that. I remember being in Serbia, and there was all this core lying out, and it was raining, and everybody was upset because it was no fun. But actually, wet core is more fun. You can see more in it,
When
and you
it's
can see that
wet.
all of the particles had been aligned, and it's because there was all of these bubbles that were streaming up through the rock to go and make a porphyry deposit up on top of it. But down in the guts of it, you could see all these processes. So, it's almost everywhere you go. If you look for the dynamic components, they're not static components, not static rocks. There's processes that are trapped in there, and that's what excites me.
Thank you. Yeah, thank you so much, Craig, for joining. It's yeah, amazing having you here.
Oh no, you're gonna ask me to show my favorite rock.
Oh yeah, your favorite rock.
Okay, what I do have is my WA subby holder collection, and I just wanted to share that with everybody. Is that
Oh,
I've got this one from the Hotel Rottnest, which of course
Hey, good
is an
spot that
awesome place
one.
to be, right? And there's my woolly one, my Woolnuff one from that's
nice.
the Student Undergraduate Society at University of Western Australia, one of my favorites. And then there's of course this one here from the what's that the Central Hotel
Leonora.
in Leonora.
Nice. Yeah,
Yeah,
Nice.
Australia
I think
represent.
this was my first stubby holder ever.
We love them down here. Yeah.
Mm,
That's so good. Thanks for showing us.
nice.
I love that so much. Well, no, thank you so, so much, Craig, for joining. If you want to share your screen and we'll get stuck into it.
All right. Thanks everybody for spending some time here with me. It gives me an opportunity to talk about something that I feel very strongly about, and I think the title sort of says it is really it's about the opportunities that come in this model space. You know, models are, you know, you could look at them as being cut and dry, and you hear people saying, I never use models, and I feel sorry for them because geology is full of sparse data and you need something else that fills in all the gaps, and that's what a model does. But models don't have to be static either, they're dynamic. They should be changing all the time with new observations and new discoveries. And so that's really part of the messaging here is that this intrusion-related gold space is a place where models hadn't been developed but needed to be developed. And once you develop them, then you can reap the benefits of having a good one or a better one than your competitors. The background there is just a ZTEM, which is something I've fallen in love with in the last few years. It's one of the best mapping tools out there, and it's pretty easy to see where the intrusions are. So if you're looking for intrusion-hosted deposits, then this is the type of geophysics that's going to find the intrusions for you. Yeah, I'm giving this unaffiliated. I don't really have a real full-time job right now, but a lot of what I'm going to be talking about is through opportunities I've had to be part of amazing organizations, amazing institutions. We're all really the product of the institutions that we've come from, and we need to support these places. I cut my teeth really at the Yukon Geological Survey, where I did a lot of mapping and first got into these intrusion-related systems. Was able to partner with the Mineral Deposit Research Unit at UBC when guys like Tim Baker and Jim Lang were there, and they are huge components in developing these models. John Thompson as well was the director at MGRU at the time. I subsequently went to MGRU and became director there myself for 12 years and got to expand on a lot of the earlier research. I did my PhD at University of Western Australia with Dave Groves at the Center of Exploration and Targeting. And I'm currently as a director and chair of a company called Snowline Gold, and we're out there exploring for these things and actually being quite successful. So it's come full circle in many ways, and there's a great story just in that, but that's another time. There's, you know, as geologists, we're attracted by shiny things, and if there's something that's not shiny, then we're attracted to anything that's red, right? And so we love a red blob. We love a red blob on geophysical maps, and we love a red blob on a geology map. And so we have this tendency to be distracted by these red blobs. And so if we see a map with a number of gold deposits on there, and then we see a red blob, we immediately want to make that association. So there's this natural tendency for us to pick the easy route. That's just our DNA encourages us to be lazy, and that's what we do. But if you were to look at those deposits, you would find that they are all the same, but they're at different distances from the intrusion. So if you're at different distances from the intrusion, you should be going into a cooling trend, and so the nature of that mineralization should change away from the intrusion. But if it's all the same, that's telling you there's another process that has a broader geothermal gradient associated with it, and the intrusion isn't the mineralizer. So that's the case here, where we have a granite, we have mineral occurrences, we have got placer gold, but this is a case where it's all orogenic gold. And that's part of the theme today too, is that we're going to be seeing places where it's hard to distinguish between the importance of an intrusion-related gold system versus a orogenic gold system. And here's another place where that happens, right? The Pataz-Barcoy districts in Peru, again, big, huge, long red batholith. Everybody, well, not everybody, but there's a number of publications that have emphasized the fact that these are intrusion-related gold deposits. They're hosted in the intrusion, but actually the mineralization themselves is tens of millions of years younger than the intrusions. It's not related at all. But this is, again, part of our natural tendency. And even going further, some of the biggest deposits in the world, like Muruntau and the Jiaodong Peninsula, things like Malartic, these are all deposits that have been published as being intrusion related, but I don't think any of them are intrusion related. I think most of them are orogenic. So it really emphasizes that just because there's an easy granite there doesn't mean that there's a genetic association. And why that matters is because when you're exploring, if you think it's an intrusion-related deposit, you should be looking for the intrusion as the source. But if it's not, then the intrusion isn't the source. It might be a potential host, but it's not the source. So understanding the models, I think, does influence your exploration decision making. And of course, intrusions are amongst the greatest contributors or hosts for gold in the upper crust, right? Here's a couple of good examples of good bona fide intrusion-related gold systems. Fort Knox in Alaska, there's at least 12 million ounces of gold that's recoverable from that intrusion, and that dotted line shows the top of it. And then one of the places that influenced me quite a bit when I was a younger geologist was going to Boddington and seeing this massive amount of gold that's in this intrusion there. And it's not a porphyry, but it sort of looks like it could or should be a porphyry, but it's not. But it's definitely intrusion-related gold system. And so one would think that there's a rich literature about intrusion-related gold systems, but when you look at the foundational documents on gold model or on models, right, such as the USGS deposit models of Cox and Singer, the Geological Association of Canada ore deposit model volumes, the British Columbia Geological Survey mineral deposit models, even Economic Geology 25th or 75th anniversary volume, none of them have any papers in them emphasizing the characteristics of intrusion-related gold models. They have things in there about porphyries or about skarns that are related to intrusions, but there's nothing that's a separate category of intrusion-related gold systems. Compare that to what we now call orogenic systems. There's a rich literature, right? There's mesothermal gold, there's papers on greenstone gold, papers on Archean gold, turbidite gold, shear hosted gold. Every setting that orogenic gold deposits occurred in was essentially a different model. So, a rich characterization and classification over on one side of the gold space, but the intrusions, it didn't really happen that well. And so what's the reason for that? Was it that I'm suggesting that probably part of it was that there's a lot of inconsistencies in the way that the ore systems present themselves. And those inconsistencies maybe make them not so predictable. So I think that variability has been a part of the issue. And we can go through a thought experiment, right? Let's say we're looking for intrusion-related gold system models. Okay, well, there's 3 magma types that represent different source materials and crustal settings, I-type, S-type, and A-type. And let's just say there's an intrusion-related gold system potentially associated with each one of them. So that's 3 potential different models by association with the magmatic type. But we know that the metals in these things can fractionate, or the crustal levels can change as a result of fractionation. So then we have I-type fractionated, unfractionated, S-type fractionated, unfractionated, etc. So we potentially have 6. But then we also know that oxidation state is a key component as well. And so here we've got 12. And we could throw in other variables such as alkalinity, depth of emplacement or something. So there really is a wide range of environments where gold or where intrusions could be potentially making fluid that could form an ore deposit. So I think that part of that variability in nature in terms of the source of the intrusions themselves, the crust that's coming into alkalinity, blah, blah, blah. I think that there's just a high degree of variability, and our ability to make intrusion-related gold system models seem to be better at more of a district scale. So that might be part of the punchline here. When we look at some of the models that were proposed, such as the intrusion-related gold deposit model by Silito, that was mostly associated with porphyry systems, I-type granites, breccias, skarns, these sorts of things that are mostly in that porphyry space. And same with eventually there was something called gold-only porphyries, and then eventually there was something called plutonic-related gold, and that's where all of the proximal the nearest intrusion to a lot of mineralization in Alaska was all lumped together under this plutonic-related gold model type. And here's a cross section that they published, right? So there's a wide range of things, different crusts, right, or different depths within the crust, different relationships to the intrusion, lots of variability, not a lot of similarity, which you need in order to make a robust model. The 1998 paper by Thompson and Silito and identified a number of different gold veins that they thought to have been associated with a proximal intrusion, including Shandong, Pataz, Dongping in northern China, Ryan Gold. I think all those things are orogenic. So, you know, even within, these are really, really smart people. They've seen a lot. But I think there's also ways to look at these things as maybe not really fitting that model really well. And I think a part of what they came up with is recognizing we need to understand the differences between what can just be intrusion hosted versus what is intrusion related. And when we say intrusion related, mostly we're talking about genetic association. But things started to change and move into a more interesting space with a paper from Thompson and Silito, where they introduced the concept, a model, intrusion-related gold with tin and tungsten. This was the first recognition that gold deposits could potentially occur in a setting different than porphyries. There's no associated copper. The plutons tend to be more reduced, more felsic, more paraluminous, more looking like an S-type granite, and having that lithophile metal and element associations. So that was an important feature. And then shortly thereafter, Jim Lang, Tim Baker, myself, and Jim Mortensen published a paper in the SCG newsletter that looked at these types of systems as we saw them in Yukon and Alaska. So this is where a large number of discoveries were being made, exploration was being done. This deposit, Fort Knox, was getting into development, and there was other advances. But the thing that we recognized, again, there's a tremendous amount of variability, so we didn't want to call it intrusion or deposits because it wasn't one thing, it was systems. It was all of the fluids as they're escaping from the intrusion are reacting with the country rock and forming different styles of mineralization. At a Roundup conference in 2000, there was a volume that came out that was dedicated to the Tintina Gold Belt, and that was this big, broad arc of northwestern North America, where these deposits were being found in Yukon and Alaska. And this volume, it's a great volume if you can get your hands on it, but it sort of made the Tintina Gold Belt synonymous with intrusion-related gold veins, which is fine, but there's some papers in there on deposit types that are not intrusion-related, but they've been sort of assumed to be intrusion-related, like Pogo and Donlin. So there's, it's easy to see how these things can be misinterpreted. And here's just a picture of, Yukon and Alaska, 1,500 kilometers across. And we have this huge thing called the Tintina Gold Belt, or I call it the Tintina Gold Province, because it's really a composite of a large number of gold districts. And a large, and we should recognize that some of these gold districts are intrusion related and some of them are not. And many of them, for example, are placer districts or are related to orogenic gold districts. So distinguishing between these things really is key. Also in 2000, lots of things were happening then. Thompson and Newberry published in the Gold in 2000 volume the first time we actually said the word reduced as the title to the model. So this reduced intrusion-related gold model was introduced then, emphasized the low oxidation state of the associated intrusions and clearly distinguished it from all the intrusion-related gold deposits that had been characterized in the earlier literature. Also that time, Steve Rowans introduced the concept of reduced porphyry copper systems. And they really are porphyry copper systems, but because they're reduced, the copper doesn't mobilize or deposit that well, but the gold does. And so I think this is a really interesting variant that there's not a lot of them, but I have seen some that fit into this model quite well. So when you start putting all these words and concepts and models and classifications together, it really is a mess. And I haven't even started talking about the alkaline intrusion associated deposits, which are also their own mess. And so we need to have some sort of structure that we can better understand these things. And you're lucky because I'm here to help. So when I look at this model space to classify these things, I sort of like to use the redox as a foundation. So on the left-hand side, we have these deposits that we'll talk more about just shortly, called reduced intrusion-related gold systems. I've put the reduced porphyry copper model there. And then on the right-hand side, we have mostly what are porphyry copper deposits. Some of them are gold rich, some of them might be gold only, some of them might have alkaline associations, but they are on that far right-hand side. Just to make it easy, we'll get rid of a couple of the more extreme members, and all these gold porphyry systems, just as lump them into something we're going to call the oxidized clan of intrusion-related gold deposits. So now, when somebody says to you, what's an intrusion-related gold, or what sort of thing are you exploring for? And then they say, I'm exploring for an intrusion-related gold deposit. Right now, people just nod and go, oh yeah, right, sure. But no one really has a clue, right? Is that it's all over the map. But the first thing you should be asking is it an oxidized system or is it a reduced system, right? That will immediately tell you what end of the spectrum that you're on. Besides oxidation state being a key variable in the characteristics of these two end members, crustal depth is also really important. As we know, all of those porphyry occurrences are forming at 1, 2, maybe 3 kilometers depth for the most part, and they have a lot of characteristics that show a huge fluid volume reacting with the crust, and the fluid is winning, right? There's textural destruction, the fluid might even be talking to the atmosphere. In these reduced systems, what happens is you're under so much lithostatic pressure that the fluids, once they generate, they don't get out and they don't change their composition. They don't become acidic like the oxidized fluids do. They are just deep within the system and they have to flow along fractures, and there's not a huge fluid volume, and so you don't get a tremendous amount of alteration. So there's very, very different characteristics about these styles of mineralization that go beyond the redox and go beyond their crustal depth, but those things combined sort of define these end member classifications. Now that we're talking about redox, I get to talk about a friend of mine who died recently, is Shunso Ishihara. He's sort of the father of redox and granites, and emphasizing the importance of how intrusions respond differently to redox. I was fortunate to take him to a trip through Yukon, Alaska some time ago, and a big part of the concept that he came up with was distinguishing that there's not just intrusions, but when you're talking about intrusions, are they magnetite or are they ilmenite granite series? And he figured this out with just a simple handheld magnetic susceptibility meter. Right here he was invited to Eastern Australia, and he zapped every granite that he could get to, 825 zaps. And what he found is they come out as two different populations. And when he followed that up with petrography, he recognized, well, all of the ones that have high magnetism obviously have high magnetite, but those ones that have low magnetic responses, they don't have any magnetite at all. They're full of ilmenite. And so this is the fundamental classification of intrusions, is we want to know right away, is it a magnetite or is it an ilmenite series granite? The reason why that's important for explorers is because of the redox state that influences these minerals also influence the magma's ability to be enriched in different elements. The oxidized ones are obviously have high sulfur mobility, but these are the places where you're going to be getting lots of copper, lead, zinc, associated silver, as well as gold. Whereas the reduced ones, you have that stronger lithophile connection, looking at tin, tungsten, beryllium, maybe even lithium is more closely associated with these things. So from my perspective, it's a first principles classification, the redox is, to the mineralizing potential of your targets. And we're going to come back to this again. I can't remember why, to be honest. Oh, there we are. So when we get into this Tintina gold belt, for example, okay, we can see all of these deposits that I've emphasized here, right? There's Fort Knox, Golden Summit, Live and Good. These are all intrusion-related gold systems in the Fairbanks area. And then when we go down the Tintina Fault into Yukon, 450 kilometers of strike slip displacement, we have this other belt that comes through here that we call the Tombstone Belt. And this is a place where we have Eagle Gold, previously known as Dublin Gulch, Ormac, and recently discovered Valley deposits. So This magenta color that's on the furthest inboard position with respect to the Tintina gold belt, that's where we get these intrusion-related gold deposits. And they're all associated with reduced intrusions. The other characteristic, as we've said, associated with lithophile mineralization, it's also a place where we have some of the biggest and the richest tungsten deposits in North America, or most of the world outside of China. And so there's a strong association of these reduced intrusions with scheelite in particular, and mostly as skarns. And so even though we have gold systems here, the gold systems are formed from the same intrusions that are forming these scheelite deposits. It's also a district that has a high silver tenor. There is a district here, Keno Hill, for example, where there is far more than 220 million ounces of silver that's being produced in a belt that has these reduced intrusions in them. And so let's just look at some of the reduced intrusion-related gold systems and how they look. This one's called Dublin Gulch. It's in production right now. This is a picture, though, from about 20 years. You can see the ridge of the hill is actually where the intrusion is outcropping. And then down on the slopes, we have Hornfels. And then as, of course, all that's eroding, we've got this creek that's full of gold and scheelite. This is what it looked like last year, maybe 2 years ago, as they first started going into to start the mining. You can see it's slightly oxidized. The mining originally was run-of-mill. It's on leach pads. They're crushing it now that they're getting deeper into the rock outside of the oxidation. And as a map pattern, it sort of looks like this. It's an elongate intrusion. It's a few kilometers long. It's surrounded by this odd shape of biotite hornfels and has a couple of associated skarns with it. As I mentioned, there's the placer gold that's coming out of it. There's a location called Tin Dome that's again emphasizing this lithophile association. There's a tungsten skarn right next to it. There's a large number of gold arsenopyrite veins that are in the hornfels. And then within the intrusion itself, we have these mineral deposits that are formed by sheeted vein arrays. These are individual veins, maybe 1 centimeter thick, but they go for a couple of hundred meters, and maybe tens to hundreds of meters in width. And these arrays they're dead parallel. They're not a network. They're not a stockwork. They're just a fracture array that are dead parallel to each other. So we call these sheeted vein arrays. And these things, the individual veins might have grades of 10 or 20 grams, but when you combine it with all the adjacent veins, you end up typically with a grade that's about a gram. And then more distal to this, we have silver lead zinc veins. Cross section, you can sort of see the mineralization is preferentially in the uppermost part of the intrusion, the apex of the intrusion. And this is what's being preferentially mined, but you can sort of see we've got grade down here about 600 or 800 meters into the top part of that intrusion. We go across into Alaska, look at a very similar situation at Fort Knox. You're right at the top of the intrusion. You can see that white line as being the top of the intrusion. This was probably about 20 years ago. When it first went into production, it was 186 million tons of 0.93. It has a very large mill that started off as a 30,000 ton per day mill, bumped up to 45,000 tons per day, producing 300 to 350,000 ounces a year. So pretty remarkable. It's now, I think, at just having its 9 millionth ounce produced. And again, when we just look at it in a civil geology plan, it's a small elongate pluton, has multiple phases within it. Nothing very remarkable, but we do get these pegmatites and aplites that are forming in these parallel zones, and it's within those parallel zones that we get these sheeted vein arrays. So the pluton, the different phases, the dikes that are associated with it, and the mineralization are all being accommodated in this east-west sort of extensional array. This is just a bit of a pit map, and you can see there's some structures there. And then when you look at the blast hole data, all of those, the red there is sort of essentially greater than a gram. So you can see there's very strong structural control at this deposit as well. That's helping to sort of enrich and focus the density of those small veins. So this is what the rock looks like, the ore looks like rather. It's not very spectacular. It just has these fractures with these skinny veins in, 1 millimeter to 1 centimeter. Very, very narrow alteration salvages, if at all, and not any whole-scale alteration. And you can see the veins essentially are all parallel to each other. There's a late shear coming through here, but that's not connecting the veins. The veins generally are not connected. When you get down and dirty with those veins, the gold occurs as free gold, and almost always it's associated with these silvery or dull gray minerals. And when we look at those minerals, we find the same relationships at all of these deposits. They're all exactly the same. The gold is touching minerals that are high in bismuth and high in tellurium. Our thinking is that at high temperatures, the bismuth, tellurium, and gold is traveling as an alloy, and it gets deposited as an alloy. But as the temperature decreases, the bismuth in particular is very unhappy, and it pulls itself out, and it forms either native bismuth or bismuthinite, and it leaves behind a bunch of residual tellurium. And so we find that the association is always bismuth, tellurium, and gold. Here's some additional reflected light photographs. The top left one is from Fort Knox, and there you can see it interleaved with a bunch of molybdenum. And here's a grain here where most of the gold is exsolved out, but you can sort of see there's a bunch of gray in here. This is mostly maldenite. And so maldenite would probably have the closest stoichiometry to the original alloy. But the low temperatures, almost always, there's very high efficiency in extracting the gold. Another example, right, the gold is all out here in the fractures, but we have all this bismuth and tellurium minerals over here. Same situation over there. The gold mostly occurs just as native gold. And when we look at the mineralogy here, it's almost all, bismuth and tellurium minerals. This was some of the first chemistry that I did 30 years ago or something on these things, just to find out what the relationship was. And again, we find this very, very strong gold bismuth relationship, usually 20 to 1 for bismuth to gold. We find this very strong tellurium gold relationship, almost 1 to 1. And scheelite occurs in every one of these samples, and it's hard to see, but if you get out your UV lamp, you can see it, no problem. No correlation. So scheelite is an essential part, an essential mineral of the veins that are being deposited, but it's not doesn't have any obvious relationship with gold. Just some more examples of the high temperature part of the system. These are this is a anhydrous skarn at the top and a hydrous skarn down at the bottom, and you can see a similar sort of thing again where the bismuth, tellurium, in this case with antimony, are forming all of the late infilling with little bits of VG everywhere throughout. And again, this bismuth, tellurium, gold, and tungsten relationship in both cases. This is fine work from John Mayer, who did his thesis up here in the Yukon. And sometimes the fluids don't stay in the intrusion. Sometimes they go out into the wall rock, into the country rock, into the Hornfels. And so sometimes we have tremendous amounts of anomalism or enrichment in the adjacent rocks that are adjacent to the intrusion. And in those cases, we have Hornfels. Here's a biotite Hornfels with pyrrhotite. We have a number of veins that are in here. These ones were antimony. And then the ones with arsenopyrite, they have little bits of free gold associated with them. So that's emphasizing that the host rocks that host the intrusions are potential hosts for mineral deposits. And these Hornfels are usually so well enriched in the arsenopyrite that that's amongst the easiest method to find an intrusion is you just look at the regional geochemistry to find out where the arsenic anomalies are. And that's telling you exactly where all of the Hornfels is. So it's telling you where all the intrusions are. And so every one of these blips that is based on arsenic geochemistry from stream sediments, there's an intrusion. So when we put all these components together, we have something that we think can be a model, right? We see similar sort of features at many of these occurrences. And so we always end up with a small elongate pluton. We have associated aplite and pegmatite dikes that are in the same orientation as the long axis of the pluton. We have this large misfit Hornfels, and that's telling us that there's more pluton underneath that is forming this Hornfels zone. It's not coincident. And so that as well tells us that we're towards the top of the intrusion, so we're near the apical part of the intrusion. And then, of course, rocks being opportunistic in terms of being mineralizers. Here we see a skarn being developed because there's calcareous rocks. And then, for example, if you have thrust faults or any other structures there, the fluids could potentially be focused along there. We do get rare breccias, but mostly we're too deep. So the kind of confining pressure is too high, so we don't get a lot of breccias, but we do get replacements and disseminations within the Hornfels zone. So styles of mineralization would look like this. We have sheeted vein arrays within the intrusion, skarns as you go out, arsenopyrite-rich gold veins that are usually Hornfels hosted. We get outside of the Hornfels and we tend to get antimony associated with gold veins. And then when you're further away, you tend to get lead, zinc, silver veins. So when you look at the chemistry from, say, soils or from regional stream silts, we typically will always get this zonation, right? Where you have gold, bismuth, tellurium, and tungsten while you're in the intrusion. This is a sulfur poor area. As soon as these fluids get into the Hornfels, they start seeing a lot of sulfur and arsenic, and so we get a tremendous amount of arsenopyrite. Further beyond, we pick up the antimony, and then again, further beyond, we have that lead, zinc, silver signature. And there's no scale here, but normally the intrusions that we're looking at, we want them to be about 1 kilometer. If they're smaller than that, that might be good because you could just be a small apical part of it that hasn't yet eroded. But you want to have enough volume there that it's giving you enough heat and enough potential fluids and enough potential host material for deposits. But if they're really big, we find there isn't much focusing and maybe you've eroded too deeply into the intrusion. So by the time you're at sort of 3, 4, 5 kilometers, then we think that the model doesn't work so well. Here's just a cross section. Again, we have that Hornfels aureole, and you'll see how it's pretty skinny on the sides, but it's high up at the top. Most of the heat is being lost up through the top. The first bit of the heat loss within the intrusion is going to cause crystallization of a cupola, right? And that's really important because that rock has to be brittle enough to fracture when the fractionating magmas make a fluid. So we need to have that heat loss. We need to have that brittle carapace right on top of the pluton cupola. And it may also be, as it is with porphyry systems, is that the volume of magma here really isn't sufficient to generate enough fluid or enough gold, and that it might actually be connected to a mid-crustal reservoir that is actually using this pluton, this sort of cylindrical body, as a conduit, where the fluids are being derived in the batholith and then are bubbling up or are being channeled up through fractures or dikes to a point of mineral deposition. So I've emphasized that this vertical component is really important, and we see that as we get up high in the system that the styles of mineralization are dominated by arsenopyrite and antimony and are sometimes refractory. The best style of mineralization we see are typically deposited down to that 5, 6, maybe 7 kilometers in depth in the upper part of these intrusions, and then as you've eroded down here is probably your chances are significantly less. So depth of erosion is important, and understanding how the relationships between the cupola and the carapace are also important. But we know from examples where there has been deep drilling that these carapaces sometimes are 1.5 kilometers thick. So there's quite a bit of space to play with there. So I think we've gone through many of the components associated with that model. I'm just going to talk about a few things where things have expanded beyond the model, or where I'm seeing new opportunities developing just by, keeping an eye on the literature. And now that we know that there aren't good intrusion-related gold models out there, you can start putting your own together. And so keeping on top of the literature, press releases, some interesting things can happen. But first, I'm going to start with some things that I know quite a bit about. This usually those sheeted vein arrays, we would typically get 3, 4, or 5 veins per meter, and that's what would typically give us 1 gram per gold. There's been a new discovery in the Yukon, a deposit called Valley. It's not a deposit yet, there isn't really a resource, but we have super high vein densities, right? We have 10, 15, 20, sometimes 30 veins per meter. And when you get that high vein density, you have more quartz. When you have more quartz, you have more gold, gold, bismuth, and tellurium. So we have as a result of those high vein densities, we have exceptionally high grades for these systems. Systems that are normally, gram would be good, but sub-gram. In this 36-meter section, for example, it's 4.2 grams throughout. And this is on top of a 121-meter section that's 4.1 grams. And this is within a 418-meter drill hole that's just almost 2 grams directly from surface. So these are grades that we never anticipated in this model, and this is just as a result of a new discovery. So it really opens up the space within the model to try and accommodate this and potentially other deposits. This is just a cross section from there. You can sort of see on the left-hand side, that's all Hornfels. The grade is all entirely within the intrusion. In this case, within you're up against the southern margin of the intrusion, but incredible intersections. 384 meters of 2.47 grams per ton, 4 grams in the top 120 meters. Here's one 553 meters of 2.5 grams. Anybody who knows the CN Tower in Toronto, that's about 550 meters tall. So if you can imagine that thing being continually mineralized at 2.5 grams, like that's the size of the opportunity that we're looking at within these intrusion-related gold systems. So my colleague Rich Goldfarb likes to poo-poo these things because they're typically sub-gram, but this is really telling us that the model has a tremendous amount of room to grow to try and accommodate these grades and these enrichments. This is the Valley deposit over here on the left-hand side, and we can sort of see where it's exposed. There's about a 1 kilometer wide intrusion. And most of the mineralization is pretty tight within a couple of 100 meters of that edge. A few kilometers to the east, we have found a location that is Hornfels that's about 5 kilometers long and has gold mineralization or gold enrichments indicated in the soils above it. This is not an exposed intrusion. This is where the geophysics is telling us there's a resistor at depth. But this is really sort of starting to tell us about the size of the thermal and the hydrothermal expression of these systems when you're above the intrusion. And I think this is really interesting because we're seeing new deposits being going into resource that have very large numbers and they're not in the intrusion. So this is really emphasizing a tremendous amount of new space that is above these intrusions. And a good example of this is the Golden Summit deposit in Alaska. All categories in, it's about 20 million ounces of I think that's 0.88. And we can see probably only 1/4, maybe a fifth, is actually in the intrusion. And the rest is off beyond the intrusion in the Hornfels. So this is pretty exciting, I think. In the Yukon, there's been successful drilling that something that was 4 individual deposits is sort of morphing together so that they're all joining up. And we've got a new resource on this Ormac deposit that's telling us there's about 7 million ounces in this, and there's no pluton exposed at all. And we can see, and when we're in distal environments away from the intrusion, it's the host rocks that are reacting. So we're getting, within this Hornfels area, there's heat, there's energy, there's enough fluid that's causing reaction within the Hornfels, and replacement and gold mineralization. So this is an important new space, I think. We've focused the intrusion typically, but I think that this Hornfels Oriole, it was misrepresented in the figures that I'd published previously, and now it's something like this. It's got to be at least 5 kilometers across of potential rock that's being modified and potentially mineralized, and we don't really have a good idea about what that vertical component is. But that's a new space for this model that that really hasn't been well characterized or documented. Another place that I think is super exciting, and I don't know enough about it, is the Pattison Range in northern WA. You know, the Telfer and Nifty we've known about for a while as being odd ducks. We don't know where they fit into model space at all, but the discovery a few years ago at Waiinu was really interesting as well, and emphasized that maybe we can put a model together. And then more recently, the Havieron deposit was discovered. So now we have, you know, 4 deposits. They all look different, but there must be some way that we can find like characteristics associated with them and use that to form a basis for better decision making in this area. I think it was great when they put the cross section together. They showed, you know, these are the non-magnetic granites and these are the magnetic granites. And actually, what you see is there's a lot of complexity between the relationship between the oxidized and the reduced components of the magmas. So they're really, I feel there's a model that needs to be developed here that it could be an asset for discovery here. And the great thing about this Waiinu model, again, I'm going to come back to this, is that early on, in the early fluids, there's scheelite and a bit of moly. A little bit later on, there's bismuth, there's maldenite and gold. Where did we hear about that before? There's bismuth, there's telluro-bismuth. So it's, again, that strong gold, bismuth, tellurium signal is associated with this. The thing that makes this different than a lot of intrusion-related systems is that there's this late overprint of chalcopyrite, and it's rich with chalcopyrite. So it's telling us something really interesting about the processes there. And then Havieron, it's underneath a lot of cover. It was a mag anomaly that was just some aggressive drilling to go and get to it, and it's pretty exciting as well, right? There's lots of gold there. It's got a little bit of a sniff of copper as well, but this is in a breccia, and we don't see the intrusion, but we anticipate that this would probably be above an intrusion that's gassing off and then using that brecciated conduit to push fluids up closer to the surface where the mineralization is happening. So I think it's a super exciting area. Another area I'm kind of looking at is in Brazil in the Paleoproterozoic. Granites everywhere, as you can see there. There's Monza granites, there's granodiorites, there's cyanites, lots of potential targets, but there's a large number of styles of mineralization in there that that look pretty interesting. This one locality in particular, Tocantins, Zinho, Eldorado Gold had it, sold it to G Mining, and they're developing it right now. They're doing a great job. But you can see some of these intersections, 47 meters of 8 grams. Like, that's going to make money. You know, 170 meters of 1.84 grams, right? This is in this quartz monzonite body that has some structural control. But you know, it looks pretty interesting to me. And the thing that looks interesting to me is that it's not just this one place. I see numerous companies in this district publishing press releases that show similar characteristics. And so I don't know that there's a model here, but I suspect there should be. Key in this is that these Monzo granites, or you can sort of see there is quartz in these things, lots of pink alkali feldspar. The alteration that comes through, it replaces everything with an additional generation of microcline, of potassium feldspar, and you end up with these wormy little strange features that subsequently can turn into quartz veins, or they're overprinted by sort of a chlorite pyrite alteration that forms, these reasonable, that has these gold enrichments. And then a couple of months ago, there was a press release that came out from somewhere 1,000 miles away in southern Brazil. And guess what? It's looking very similar as well. It's got this strange um, alteration that eats away at the feldspars and the quartz, and then deposits a second generation of feldspar, and then the last gasp has this pyrite and chlorate in it. So, like, I think this is another example where a model could or should be developed, and it's all kind of within this intrusion-related clan, but it's different than the models that we know so far. So, just to wrap up here, I think exploration success for intrusion-related gold systems has been hindered because we haven't had good models and we haven't had good classifications, and so we don't have good ideas about what the ore bodies that are hosting these things, could look like. I think within the existing models, as we've indicated by that valley deposit, there are places where things can expand and maybe look differently than we thought of them before, and that just again emphasizes that models can't be static. They need to be dynamic. They need to be changing with new discoveries. And that I think in your new districts in particular, develop your own models. I think there's a big opportunity to like a competitive advantage to actually developing your own model because you know more than your neighbors do, or you're paying closer attention to the literature or to press releases that are coming by. And the thing that I'm seeing is that these models do tend to be district specific, as we've talked about the diversity of the intrusions and the fluids and everything like that. But it seems to me that when you're within one district, and I mean that in the biggest sense, that there's the same processes that are potentially happening over and over again, and so you're better to build a robust model that's based on that belt. With increasing gold price, we're having decreasing cutoffs, and so things that before we never thought would be ore or could be ore are turning into ore. So there's a whole bunch of sub-gram model opportunities, I think, that could be considered. And last thing I'm going to say is I think we need better tools to understand the Hornfels regime. As I've indicated, these are potentially big volumes of rock, but we don't understand when we're in there where the cold parts are, where the hot parts are, who's seen the fluid, who hasn't seen the fluid. I've seen recently some good work done on graphite crystallinity within Hornfels that maps out temperature regimes, for example. So I think there's some opportunities to understand that volume of space as well. And that's it. Don't hesitate to send me an email if I don't get your question answered today.
Thank you so much, Craig. I really appreciate it.